Hello guys, welcome to Stats with Warnke. Today we'll be covering all of these learning targets, kind of wrapping up our examples for the notes packet. So this is kind of an accumulation of everything that we have been doing so far in this section. Here is the first example that we're going to do today, the one of two that we are going to cover that we have left in our note packets. So reading that first paragraph, it says, many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause higher achievement, or do better students simply choose to sit in the front? Reading that, we can pick out what is our explanatory variable and what is our response variable. So our explanatory variable is what we use as our x, what we measure, and then use that to kind of help explain the other one. So in this case, we're talking about seat location is what we're going to use to explain test scores. So seat location, that row, is going to be our x, and then the score is going to be our y, our response variable. That's what we'll measure. And then down below it says least squares regression was performed on the data. A scatter plot with the least regression line was added, a residual plot, and some computer output from the regression are shown below. So here is our scatter plot and our residual plot. We will be referencing those as we go. And here is our computer output. The first question says, what is the equation of the least squares regression line that describes the relationship between row number and test score? So to figure out our least squares regression line, we're going to look at that first column with numbers in it. This column over here is kind of like our heading. We have our constant and our row. Our constant, and that we trace that over to coefficient, is 85.706. That is our y-intercept. That next row down says row. That is because that is our x. So when you look for our computer output, you look for x, and that is going to be in this case our row number, and then we trace that over, and that gives us our slope, negative 1.1171. Putting those two together, we can write our equation in slope-intercept form. It looks just like here for letter A. When we write our equation, we can use the variables, in this case score and row, to represent our inputs and our outputs. Because we're inputting the row number, we're predicting the score. You can also use x and y. If you choose to use y hat and x, you need to define those below. For question B, it asks us to interpret the slope. So looking at our slope, we see that is 1.117. So that's change in y over change in x. Our change in y is that we're going down by 1.1 approximately, and for every 1 that we increase in x. So for our interpretation, each additional row from the front of the classroom, we predict a decrease of 1.117 points on the student's test score. I'll have all of these linked on Canvas, so if you don't have time to write down all of these, I'd recommend you pull up that Canvas document and copy these down and just kind of follow along with us as we go through the video. For C, it says to find our correlation coefficient. And so we have, from our computer output, you can see that r squared column, our r squared value is 0.047. So if we know what r squared is, we can take the square root of that to figure out r. Because we applied the square root, this could either be a positive or negative value, so we look at the association. You can also look at the slope. If the slope is positive, this would be a positive number. If the slope's negative, this will be a negative number. Since the association, as we go from left to right, is negative, this will be negative. And lastly, for D, it asks us about the appropriateness of our linear model. We can look at the residual plot to determine that. If we have the linear model is randomly scattered and they are relatively small in size, that would mean it's appropriate. So it says, because there's no obvious leftover pattern in the residual plot, a line is an appropriate model for these data. So all of those combined together answer those three questions, or four questions. Moving on to the next one. This is our last example in the note packet. This one involves netbooks. If you've seen that, you can kind of skip over that first paragraph. If you are not familiar with them, you might want to take a moment and read that first paragraph. Down here in blue, I have the two questions that are highlighted at the bottom of the page. Should we use a linear model to predict battery life of a new netbook based on its weight? And if so, how accurate will our predictions be? The first thing we need to do is identify our x and our y, our explanatory and response variables. From that first question, it asks us to predict battery life. That thing that we predict is going to be y. What we're using to make that prediction is our weight, our x. So using those two, we can plug that into our calculator and figure out what is the least squares regression line and then some of our other information. One thing we're going to need to assess this is we should look at a scatter plot. We should also look at a residual plot. So plug these into your calculator and list 1, list 2, make the scatter plot, make the residual plot, and then draw those on your paper. Relatively small, you're going to need to write a little bit as well, but near the top, draw both of these graphs, and then perform our operations. Whenever we look at a scatter plot, we should talk about stud. And then when we talk about a residual plot, that's going to assess how accurate this our lines will be. We can talk about our standard deviation and r squared. I'm going to give you the standard deviation so you don't have to worry about calculating that, and our calculator will give us the r squared. Once you have everything typed in your calculator, it should give you these outputs. So on that top left side, we have our scatter plots. On that top right hand side, we have our residual plot. Make sure to include labels and scales for both of these. On our scatter plot, we have also included the least squares regression line. That's not something that you necessarily have to include, so don't worry about drawing that in. And then down below, we have our computer output. So here is your standard deviation. You're going to need this when you answer the parts about the accuracy of our line. And then for r squared, you also will want that. If you know what you're doing, go ahead and pause and then answer these on your own. If you feel like you need a little bit of assistance, just keep going along with us. So the first part we're going to do is we're going to describe that scatter plot. We're going to go through stud. So we talk about strength, type, unusual features, and directions. So the scatter plot shows a fairly strong positive linear association between weight of a netbook and its battery life. There is one possible outlier at 3.2 pounds and 6.5 hours. With that information, we should also give a little bit of context about what that outlier, why we think it is. And so this netbook is much heavier than the others, but its battery life is only slightly above average. We also should talk about the residual plot. Is a line appropriate? Since there is random scatter and the residuals are relatively small in size, we can say yes. The residual plot does not show any obvious leftover patterns, so the linear model is appropriate for these data. So now we just have that last question about how accurate is this. So this is where we use our standard deviation and r squared, our coefficient of determination. The standard deviation of the residuals is S equals 1.62. That means our predictions will typically be off by about 1.62 hours when you use the linear model to predict battery life from weight. Since we mentioned a linear model, we should include that. And we have it right here that our battery hat, that's our predicted battery, is equal to our y-intercept and our slope that comes from our calculator outputs times the weight. So we've used the variables to talk about what these are. If you chose y and x, you need to define those. When we interpret our standard deviation, make sure to include the word predict or predictions, because that is important. This is a model that we are using for the data, not the actual data itself. These are all predictions. And then we talk about our context, the battery life, the weight, and then we include the interpretation of S, so the typical distance from the model. The last component of this is that we will interpret R squared, our coefficient of determination. 52% of the variation in battery life is accounted for by the linear model relating battery life to the weight of the netbook. We're going to finish this problem with just one more step, just a conclusion. So, although the linear model is appropriate for this data, our predictions will only be moderately accurate. Our predictions will typically be off by over 1.6 hours, and nearly half of the variation in battery life is unaccounted for by the linear model. So this conclusion ties up everything in that problem that we have done so far. All of that work with stud, with the interpretations, with the using our residual plot, all of that comes together to say, in this situation, our line is not very accurate. We can use it, but it will not give us very precise answers typically. Thank you for joining me today. I hope you guys have a wonderful day. If you have any questions, I'll be happy to answer those in class tomorrow. Goodbye.